This video is about the carry look-ahead adder, which is a much faster adder than the conventional carry ripple adder. First of all, we remember the full adder working. We assume that the switching time of every kind of gates is the same, so we assume the delay of the XOR gate is equal to that of the OR and the AND gates. So in this situation, we have the sum delay equals to 2 gate times, while the delay of the carry is equal to 3 gate times, which is the slower path. Now we see the delay of 4 bits ripple carry adder, which is composed by 4 full adder. All the A and B bits arrive parallel as well as the first carry in, or C0. We already saw that after 2 gate times we have S0 and after 3 gate times we have the carry 1. S1 needs to wait the carry 1 plus the XOR gate time, so it takes 4 gate time to be stable. Carry 2 needs to wait the carry 1 plus and the OR time, so we have 5 gate times, and so on. At every stage we add a gate time to the carry in to have the sum and 2 gate times to the carry in to have the carry out. So generalizing for an n bits carry ripple adder, we have to wait 2n gate times for the last sum and 2n plus 1 gate times for the last carry out. As you saw, all the times are affected by the carry propagation delay, and this is the time we have to wait for having a stable result of our addition. If, for example, we have a 4 bits adder, the delay is 9 gate times, and for 16 bits adder, the delay is 33 gate times. Now, let's see if we can build a faster adder. We have to face the carry propagation delay, so let's see how the carry is produced. In the table, we see that when A and B are both high, we generate always a carry. So we can write that carry out is A times B, or A and B. Then we focus on this part here, and we see that the carry out is produced when exclusively A or B are at 1, so when A XOR B is high, and the carry in is high. So we can add this part of the equation. We call this part the generative part, because if A and B are high, we always generate a carry, and this other the propagation part, because it allows the propagation of the carry in. So we can write our equation in this way, and generalizing, we can write this. So now we have a way to calculate C1 starting from C0, A0 and B0, but in the same way we can calculate carry 2 as function of A1, B1 and C1. And remembering that we have C1 as function of C0, we can write C2 as function of C0 and A0, B0, A1 and B1. So as function of bits that we have since the beginning, all together in parallel. So, iterating the process, we can write C3 and C4 in this way. So now, sorting things a little bit, we have this situation where we can calculate every carry directly from the bits we have to add and from the initial carry. So let's calculate every carry starting from C1. The first term of C1 is G0, which is the end of A0 and B0. The second term is P0 and C0, and in order to get C1 we have to add these two terms, and this is done by putting them in OR. The C2 carry is the OR of the three terms of C2 equation. We see there is a first stage in which we produce G0 and P0, plus a second stage with AND gates, plus a third stage with the OR gates. The C3 carry is the OR gate of the four terms of the carry 3 equation. We note that the more bits we have, the more gates with many inputs we need. The C4 carry is the OR gate of the 5 terms of the carry 4 equation. So till now, as we already said, we have 3 stages of gates. The first for the production of the generation, the propagation terms. The second is the AND gate stage. and the third is the OR gate stage. So we have all our carries after 3 stages of gates, so 3 gate times. Now that we have the carries, we need the sums. We see from the full adder that the sum is obtained by putting XOR the propagation term and the carry of the previous stage. And because we have already all the propagation terms and all the carries, we have just to add another stage of XOR to have our final sum. Here we put in a box all the previous circuit and we add a stage of XOR in order to have the final result. We are adding 9 plus 12 plus 1 of carry in equals 22. The time needed for having the result stable on the output is 3 gates time of our combinatorial circuit plus the 1 gate time of the XOR stage. So we need just 4 gate times to perform our addition. So, in order to have a stable result on the output of a 4-bit ripple carry adder, we need 9 gate times, and for a carry look ahead adder, we need 4 gate times. So, we perform the operation in half of the time. Moreover, for a 16-bit carry ripple adder, we need 33 gate times, and still just 4 gate times for the carry look ahead adder, because we have always 4 gate stages, regardless of the number of bits. But actually, we have to say that the circuit becomes quite complicated, and for 16 bits we need gates up to 17 inputs.
Moreover, the delay of a 17-input gate is much more than that of a 2-input gate. Therefore, as the number of bits increase, the number of inputs also increase while still remaining the 4-gate levels. The circuit becomes complicated, it needs greater area, and it becomes slower and slower. So there is a trade-off to reach, for example considering blocks of 4 bits connected together. In this way, we keeps the maximum number of inputs of a gate at 5, and the total delay is 4 T-gate times 4, so 16 T-gate, which is less than the 33 T-gate of the ripple carry adder.
Please leave me a comment and let me know if you liked this video. Make sure you put a thumb up, click the notification bell and subscribe to my channel.